without any further delay, my name is Safwan. I'm an intern, and today I'll be reviewing the ECG basics with you. This will be followed by the practical application of ECGs in terms of its interpretation, and then some pathologies by my colleague Radwan. And so we can get started with the basics of ECG. So this lecture is more focused towards physiology. All right. So let's talk before we start. I know ECGs are hard. I struggle with understanding the physiology behind ECGs. Why are P waves up and why are Q waves down? Why is the QRS complex pointing downwards in one of the leads, but is pointing upwards in the other lead? And what do each of the the waves represent? And to be honest, when I was in first year, I really didn't get a proper answer as to what's happening behind the scenes when we look at the ECG, right? And to be very honest, it doesn't really matter in real life. So I'm an intern. I've attended a couple of years of clerkships and all that stuff. No one really asks. It doesn't really matter. At the end of the day, it's all about diagnosing the patient with the right ECG, right? However, once you subspecialize, I assume when you become a cardiologist and stuff like that, these stuff might become important, and understanding the physiology kind of really may help you cling some of the subtle pathologies on ECGs. So this again lecture is more towards physiology, and this is what I'll be focusing on. All right. So in my lecture today, I will review the same slides you have with Dr. I think his name is Harrison, and I have slightly modified his slides to to fit into my sort of objectives. And if need be, I have screenshotted his slides and put it into these presentations to make it to make it easy and to make it relatable, right? Because at the end of the day, the exam is going to come from his slides. We're going to talk about the voltage. We're going to review some of the electrophysiology of the heart that you guys I think might have taken in another session. Then we'll look at the electrical activity of the heart. We'll talk about the leads. Then we're going to correlate the electrical activity of the heart to what you see on ECG, and we're going to correlate the ECG, the electrical activity on the ECG to the mechanical activity of the heart. All right. I'm probably not going to go into this in this particular order, but the order that makes the most sense is what I chose to go with. All right, before we start, I want you to please just dissociate and differentiate between two things. All right, there's the electrical activity of the heart, and then there's the mechanical activity of the heart, right? The electrical activity of the heart is your action potentials, your depolarization, your repolarization, your action potentials, all those electronics, electrical stuff. That's the electrical activity of the heart. Then there is the mechanical activity of the heart, which is more focused on the physical contraction and relaxation. So these are things such as systole and diastole. All right. So for now, for the purpose of most of this lecture, I just want you to forget about the mechanical activity of the heart. Don't worry about systole. Don't worry about diastole. Focus mainly on depolarization and repolarization, i.e. the electrical activity of the heart. All right. And the second point I want you to think of, want you to focus on, is that I want you to look at ECG as this right here. This is the heart, right? This is the orientation of the heart. These, the white, the yellow things, they represent the electrical signals that are spreading toward, throughout the heart. And I want you to think of ECG as taking photographs of the heart from different angles. That's exactly what an ECG is. It's a visual representation of the electrical activity of the heart. So imagine that, this is the heart with all its electrical activity, and you are photographing the heart from different angles. And that's exactly what an ECG is, right? So we have someone who's taking a photograph from the left side. We have someone who's taking it from the other side, someone who's taking it from the bottom, someone who might be taking it from the back, someone who might be taking it from the front, right? So the ECG is basically you taking lots of photographs of the heart from different angles. Think of it like that. And I'm going to actually refer to this analogy when I'm explaining some of the concepts in this lecture. All right, so this is just a quick review of the electrical activity of the heart, which basically is talking about, we have two main kind of cells in the heart. We have the pacemaker cells, and then we have the myocytes or the muscle cells. The pacemaker cells are your SA node, your AV node, all right? You can say the action potential and the depolarization and repolarization in them kind of looks like this, right? It has these phase 4, 0, and then 3. So this is for the pacemaker cells. For the myocytes, for the atrial myocytes, ventricular myocytes, all of them, their electrical activity, their depolarization, their repolarization looks a little bit different. It looks like this, right? So it has the additional phase 1 and 2 as well, phase 2, which is the plateau phase. I will not go into the details of this. There's a whole another session for this, but just want to remind you guys that we have pacemaker cells and we have ventricular myocytes. All right. All right, so let's go back to the foundation block for a little bit, okay? And let's go back to a very particular electrode that you might have absolutely despised when you took it, and that is the action potential. All right, if you remember a little bit about action potential, it went like this, right? So let's say that we have a cell, right? We have a cell membrane right here. We have outside the cell membrane, we have inside the cell membrane, right? And outside the cell membrane, at resting membrane potential, we mainly have positive ions or a positive charge, for the most part. And inside the cell or inside the cell membrane, we mainly have a negative charge. All right, so this is at the resting membrane potential. And then, your sodium ions would open up and your, sodium would influx, which would make the outside negative and the inside more positive. And this is how the depolarization would spread, let's say, from here all the way to here. And it converts all the inside to positive and all the outside to negative, right? So at the very end of the depolarization, which is basically the action potential, the peak of the action potential, you have everything on the inside as positive and everything on the outside as negative, right? This is a depolarized cell membrane. Now, when we start to talk about repolarization, the exact opposite happens, right? In repolarization, what happens is the outside again starts to become positive and the inside starts to become negative. And this is how you can say a wave of repolarization spreads from here all the way to here. Okay, this is when we're restoring the charges to the resting membrane potential, wherein we have the positives on the outside and negatives on the inside. All right, so this is any cell membrane in the body. Now let's kind of focus and apply this idea to heart cells, all right? To heart cells. And before we do that, let's orient ourselves to this diagram, which has been used multiple times in your presentation. All right, which has been used multiple times in your presentation, right? So this is the same cell membrane as the ones that I showed you in my prior diagrams, right? This is the cell membrane. This is at the resting membrane potential. The positives are on the outside and the negatives are on the inside. Now, all I've done is that I've added something called a voltage meter. I don't even know what it's called because I really didn't like physics in high school. So it's just something that is going to measure the voltage across the cell membrane, right? So it has a negative electrode, which is in black here, and then it has a positive electrode, which is in red here, okay? So what it's going to do is that it's going to measure the voltage across the cell membrane, all right? So let's say that I'm going to depolarize this cell membrane. Again, if you go back to what I said earlier, this means that I'm turning the positives outside into negatives and turning the negatives insides into positive, right? And so this wave of depolarization, as you can see, is going to spread across from here all the way to here. All right, and as it's spreading, there's a difference in there's a difference in the membrane potentials at this point and at this point. So let's focus here. At this point, as you can see, the membrane is depolarized, which means the negative is on the outside and the positive is on the inside. But at this point, the membrane is still at the resting membrane potential, right? Because the positive is on the outside and the negative is on the inside. But as the depolarization wave spreads from here to here, this is going to get depolarized at the very end, but right now it's still at the resting membrane potential. Because there's difference in, you can say, membrane potential at this point and at this point, i.e. there's a difference in potential at the negative electrode and the positive electrode, the voltmeter is going to record this as a difference, and it's going to record this as a voltage. All right, so this is what is called the voltage. You do not need to know the physics details of this, but just know that because there's a difference in the membrane potential at this point and at this point, there is a voltage across the cell membrane, right? And because the wave of depolarization is spreading towards the positive electrode here, the deflection on the voltmeter is going to be a positive or upward deflection, okay? So it's going to be an upward deflection. Okay. So when the whole of the tissue is depolarized, as I said earlier, the whole membrane is depolarized, there's no more difference, right? There's no more difference between the membrane potential here and here. All of them are the same level. And so the positive deflection is just going to kind of die back down. Okay, so as you can see, the positive deflection kinds of die back down. One second, please. I'm having trouble with my mouse. One second. All right. We have a question that asks, what does the word deflection mean? Deflection is just changing from the isoelectric line. So let me just elaborate on that further. So let's say that we have a line, right? We have a straight line. Then if this line changes direction, either it goes up or it goes down, this is just known as deflection. Okay, it's just moving of the line up or down. Okay, that's what deflection is. All right. So again, when the whole of the tissue is depolarized, the wave or the chain, the deflection is going to die back down and is going to reach the horizontal line. All right. So if you do not understand this concept, that's totally fine. Okay. All you need to know, if there is a wave of depolarization that spreads from the negative to the positive electrode, the deflection is going to be positive. Okay. It's going to be upwards. So if we have a line at the horizontal axis, and then what's going to happen to the line is that it's going to go up, basically. All right. Now, in your lecture, there was no example, there was no diagram for repolarization, which is the opposite of depolarization. So I just kind of made one. All right. So what's happening in repolarization? We're turning the outside back into positive, and we're turning the inside back into negative. We're returning back to resting membrane potential, right? And so this is what's happening here. This is the same diagram as before. So the wave of repolarization with an R is spreading from here to here. So if the wave of repolarization spreads from the negative to the positive electrode, the deflection or the change of the isoelectric line, the change of the horizontal line, is going to be downwards. It's going to be opposite, right? It's logic. If the wave of depolarization that happens towards the positive electrode causes an upward movement of the line, the wave of repolarization that happens towards the positive electrode will be causing a deflection that is in the opposite direction, which is negative, right? So this is what I mean by here. And once the whole cell membrane is repolarized, there's going to be no difference between the potential here and at this point, and so the deflection is going to die down, and so the trace is going to go back to the horizontal line. Okay, is this clear so far?
Yes, it's clear.
Great. The deflection is the line on the ECG. Exactly, it's the trace on the ECG. Why it goes down and why it goes up? This is the reason I'm telling you, right? The reason why. Okay, don't worry about why it goes up and down right now, because that's the bigger picture. Right now, we're just talking at the cellular level. We're not talking about the heart right now, as a whole, Yani. All right, you're welcome. Okay, so this is a very important slide for you guys. Okay, so if a wave of depolarization spread towards a positive electrode, the deflection or the trace is going to go up. If the depolarization travels away from the positive electrode, so it's going to be going down. All right, the trace is going to go down with a negative deflection. So it's the opposite compared to the first one. Then we have a wave of repolarization that spreads towards a positive electrode. This is going to cause a negative deflection. And a wave of depolarization that spreads away from the positive electrode is going to cause a positive deflection. All right. It's all of this is just logic right now. Okay, think of it like this: when you depolarize a cell membrane, right, it's becoming more positive, right? If you look at the voltage, it becomes more positive. And so if something is being depolarized and it's going towards the positive electrode, it's going to cause a positive deflection. If something is being depolarized away from the positive electrode, then it's naturally going to cause a negative deflection, a negative trace, right? And vice versa for repolarization. Okay. Again, I'm not talking about the heart right now. Okay, I'm just talking about a single cell membrane. So do not worry about the heart. So for people who will be listening to this recording, we have a question that asks, how do we know the negative and positive electrodes in a heart? I'm not talking about that right now. I'll get to that later, okay? Now, let's repeat this part right here because it's a very important principle, all right? So if we have, this is a cell membrane right here. If we have a wave of depolarization that spreads from here towards the positive electrode, it's going to cause an upward deflection on the ECG. Let's say an ECG or a voltmeter, right? So if we have a voltmeter that's going, horizontally, whenever the wave of depolarization is spreading towards the positive electrode, it's going to go up like this, okay? It's going to go up. Now, if there's a wave of depolarization that's spreading away from the positive electrode, so we have a horizontal line, it's going to now go down because the wave of depolarization is spreading away from the positive electrode, okay? Now, as for repolarization, is the exact opposite, right? So if a wave of repolarization spreads towards a positive electrode, we're going to have a negative or a downward deflection, or tracing is going to go down. And opposite is true if a wave of depolarization spreads away from the positive electrode. So if this is the positive electrode and repolarization is happening from here all the way to here, the deflection or the trace is actually going to go up or in the positive direction, okay? Is this clear now? Can I move on? Because this is a very important and pivotal principle to understand basically the rest of the lecture. I hope it's clear, okay? So depolarization towards a positive electrode, up. Depolarization away from the positive electrode, down. Repolarization towards a positive electrode, down. Repolarization away from the positive electrode, up. All right. So depolarization towards positive means positive deflection. Positive deflection or tracing going up. Don't just memorize the word deflection, right? I just meant to say that the trace is going to go up. All right. So now we're going to move on. So you have positive and negative deflections. This is basically a summary of everything that I've said earlier. All right. All right. So waves of okay, this is a question for you guys. This is like a checkpoint. I'm supposed to have this for the lecture. So waves of depolarization towards a positive electrode will be recorded as positive or negative. Hey, yeah, I think I've emphasized on this quite enough now. All right, so select a pen. All right, so what's happening inside the heart right now? Let's go and talk about the heart, because that's what the whole lecture is about. So the electrical activity, as you know, starts, and this is just a review again, starts in the SA node right here, right? So it starts in the SA node, then the wave, so the electrical signals, or you can say waves of depolarization, because that's what an electrical signal essentially is, right? It's a wave of depolarization. Depolarization stimulates cells, right? So if we are talking about electrical signals that are sent out from the SA node, these are basically kind of waves of depolarization, right? So these electrical signals, I can just refer to them as electrical signals. They're essentially the same thing. These electrical signals are spread out from the SA node and they spread towards the atrium, right? So they spread towards the atrium like this, okay? And they cause the atrium to depolarize, right? So the atrial myocytes, the atrial muscle cells are going to start depolarizing when the SA node sends the electrical signals towards them, right? We also have electrical signals that go to something called the atrioventricular or the AV node, right? And there's a little bit of a delay here. And then from AV node, it goes to the bundle of His. And then from bundle of His, it goes to the right bundle branch and the left bundle branch, which go down into the ventricular myocyte, which has, the Purkinje fibers. And from the Purkinje fibers, we transfer the electrical signals to the actual ventricular myocytes, which then depolarize, okay? Remember, I'm talking about what right now? I'm talking about the electrical activity of the heart. Of course, eventually it's going to translate into the mechanical activity, which is systole and diastole, right? But right now we're just focusing on the electrical activity. So do not ask me, do not focus, do not worry about the systole and diastole right now. All I'm talking about is atrial depolarization and ventricular depolarization. Atrial repolarization and ventricular repolarization, all right? So again, just to review, so the waves of the depolarization or the electrical signal kind of spread from the SA node to the atrium, to the AV node, from the AV node to the bundle of His, to the bundle branches, then to the Purkinje cells, and from the Purkinje cells into the ventricular myocytes, right? And then the ventricular myocytes eventually are depolarized. So we can say that if we summate all of these electrical signals, if we add them up together, they're kind of going into the left inferior lateral direction, right? They're kind of going in this direction. So all of the electrical signals that we've talked about so far, where are they going? They're going in this direction, right? Sure, we have some that are going up, some that are going away from this main direction, but if we add them up together and we do some, physics, vector and all that stuff, we find out that the main electrical activity, the main wave of depolarization is spreading from here to here, which is basically going down the left, or going down basically in the same direction as the heart is arranged, right? How is the heart arranged? It's arranged slightly towards the left, right? And so this is where this wave of depolarization, or this kind of wave of electrical signal, is going towards, right? Exactly, as someone has mentioned, it's going towards the apex, right? All of this is pointing towards the apex along, you can say, the anatomical axis of the heart, basically, all right? Right, so this is a very important principle. Please keep this in mind, okay? All right, so just to elaborate on this further, let's say that there's a person who's standing at point A and there's a person who's standing at point B, all right? And then there's a child who's cycling from point A to point B, right? If you are standing at point A, you're going to view the child as going away from you, right? But if you're standing at point B, you're going to view the child as coming towards you. It's the same child, it's the same bicycle, but standing at point A gives you a different view of what's happening than standing at point B. If you're standing at point B, you're looking at the child coming towards you. But if you're standing at point A, you're looking at the child going away from you, right? It's the same child, but just you're looking at it from different points of view. And just keep this concept in mind as well. We will apply this later on when we talk about some of the other objectives, all right? Okay, so now in your lecture, actually, the leads were focused mainly on towards the end, but I focused on them a little earlier, because I think it might make it flow a little better for you guys to understand the other stuff. So what are leads, right? Don't worry about the terminologies or something. What are leads? They're basically a bunch of wires, right? In actuality, if you see someone who's having an ECG done, they're a bunch of wires. That's it, right? But physiologically speaking, they are made up of positive and negative electrodes. Now, where have we studied that earlier? We studied that when we looked at this diagram right here, right? We had this, cell membrane, we had the negative electrode here, we had a positive electrode here, right? So what are leads? They're basically a bunch of wires which have positive and which have negative electrodes, all right? And then they're going to measure the voltage difference between 2 points. That's all they are, right? That's all what the leads are. They're measuring the voltage, or they're measuring the electrical difference between 2 points, okay? Just you need to know this, all right? We have a couple of different types of leads, and I will talk about how do leads apply to depolarization later, but I'm just going to name the leads for now. We have a total of 12 leads for a standard ECG. We can have more, but just know that we have 12 for now. The first set of leads are called the standard leads, all right? We have lead 1, 2, and 3. As I said, these leads have positive and negative electrodes, right? And they're not imaginary thing. They're actual positive and negative electrodes. So they're two different wires. And when you're doing an ECG of someone, you have to attach these wires to different parts of the body, which is, and you don't have to know why we do it like that. Just know that it is like that, right? We attach positive electrodes to a certain body part and a negative electrode to a certain body part. And it's standardized that standard leads are attached in this particular manner, that the lead 1 will have the positive electrode on the left arm, the lead 2 will have the positive electrode on the left leg, and lead 3 will have the positive electrode on the left leg as well, all right? So if you see this diagram right here, lead 1, the positive electrode will be on the left arm and the negative electrode will be on the right arm, okay? Then lead 2, the positive electrode will be on the left leg, as you can see here. This is lead 2 right here. The positive electrode on the left leg and the negative electrode on the right arm. And lead 3, the negative electrode will be on the left arm and the positive electrode will be on the left leg, all right? So this is, I really can't explain much here. You kind of just have to memorize this, okay? You guys can come up with mnemonics if you want to. Yeah, so we kind of just memorize this, all right? So these are the standard leads, leads 1, 2, and 3. Then we have some other leads. We talked about the first 3 here. We have other leads which are known as limb leads, all right? These are known as AVL, AVR, and AVF, all right? and you can just read where are they attached. All right, so AVL, I'm just going to mainly focus on the positive electrode. Okay, so in AVL, the positive electrode is on the left arm. In AVR, the positive electrode is on the right arm, and AVF, the positive electrode is on the left foot. And I think this is kind of a mnemonic on its own because AVL, so the L is where the positive electrode is, and that's the left arm. Okay, AVR, the R is where the positive electrode is, which is the right arm, and AVF, the positive electrode is where the F is, where the foot is, and it's the left foot. Okay. So this is where how the electrodes are attached for these limb leads. We call them limb leads, LIMB, okay? AVF, AVL, and AVR. So these are other leads. Also, they have positive electrodes and then they have negative electrodes, all right? But I focus mainly on the positive electrodes. Then we have the precordial leads. The pre means in front, cordial, you can say it's the heart or the chest, I think. And so the precordial leads are always attached to the front of the chest, all right? We have, they're known as V1 all the way to V6. We attach them from here all the way to here. So as you can see here, V1, V2, V3, V4, V5, and then V6. All right. And basically what's happening is they're also leads, all right? So which means they have a positive electrode and they have a negative electrode. But when you're attaching them, we only attach the positive electrode because they have a single common negative electrode. So this fact is not super important. This has more to do with just technicalities. All right. There's no specific negative electrode for each of the precordial leads. They have one single common negative electrode. All right. Okay, so we have a few questions. Okay, so let me just repeat the earlier slide here. All right, so we have a bunch of leads, right? We have standard leads, we have limb leads, and then we have the precordial leads. In totality, there are 12. The standard leads are leads 1, 2, and 3. All right, and as I said before, leads are something that have a positive electrode and a negative electrode. In terms of lead 1, the positive electrode is attached to the left arm. In lead 2, the positive electrode is attached to the left leg. In lead 3, the positive electrode is attached to the left leg. All right, and you can apply the same concept for AVL, AVR, and AVF. All right, in AVL, the positive electrode is on the left leg. The AVR, the positive electrode is on the right arm, and for AVF, the positive electrode is on the left foot. All right, for all of these leads, there are also negative electrodes which are attached to different places, but I mainly kind of focused on the positive electrodes here because this is just pure memorization, right? What's the AV? Honestly, I'm not sure what the AV actually stands for. Yeah, they're leads. They're leads. We're just talking about leads right now. Lead 1, lead 2, lead 3, AVF, AVR, and AVL. They're just names of leads. All right. Yeah, they're different types of leads. I think it's augmented. I think it is. Yeah. All right. Okay. So these are all just different types of leads. Just And similarly, on this slide, we have V1, V2, V3, V4, V5, 6. They're just names of leads. You can think of it as names of wires, literally speaking. All right. All right. So in terms of the precordial leads, we have V1 to V6, and you just kind of have to know that they don't really have a specific negative electrode for each of them, like the limb leads and the standard leads. They mainly they have a single common negative electrode, which is known as the Wilson central terminal. It's a very fancy name. No one's going to ask about this unless he puts it MCQ directly asking about this recall question, which I think is quite unfair because no one cares about this. Okay. What does augmented mean? Honestly, I'm not too sure. The word augment just means to change or to modify. All right. And to be very honest with you, you do not have to know that. Just know that it's a name of a lead. That's it. All right. Probably there's a whole thing why it's called augmented, but you do not have to know why is it called augmented. Just know that it's there. Okay, because there are more important things to know. The AVs are the frontal leads. No, the frontal leads are the precordial leads. Okay, they're the ones in the front, basically. Yeah. All right. They're called the limb leads. The AVs are known as the limb leads, if I'm not mistaken. Okay. All right. So we've talked about the different types of leads, and all of this is just memorization. All of this is just facts. There's nothing much to understand here. But so now let's move on to, things that we actually have to understand, right? So focus on this statement right here, which says a positive electrode of the leads is what will record the electrical activity of the heart. All right. If there are depolarization waves that are towards that positive electrode, we're going to have a positive upward deflection. This is not stating something that's totally new. You guys already know this. We discussed this earlier, right? If there are depolarization waves away from the positive electrode, we will have a negative downward deflection. Negative or downward, it's the same thing. So let's kind of illustrate this. We go back to our example right here, right? So let's say that we have a child who's cycling across from point A to point B. We have a point A and then we have a point B as well. All right. So let's just replace these points and the child with something more practical, which is that we have a negative electrode here, we have a positive electrode here, and then there's a wave of depolarization here. So think of it like this. This was point A and this was point B. All right, and this was a child who's cycling from point A to point B, right? Now we've analogized it, I don't know what's the verb. We've analogized it to depolarization, which is more important for us, right? So let's say that depolarization is spreading from here to here, right? So if I have an ECG, logically speaking, where is the deflection going to be, up or down? So we have a wave of depolarization that's spreading towards the positive electrode based on what we've learned so far. It's actually, so the deflection is going to go up, right? It's going to go up. And so I put this guy right here just to show you that the positive electrodes are what are going to record the actual electrical activities of the heart. So we really worry mainly about the positive electrodes when we're going to discuss, the physiology behind the ECG. So mainly focus on the positive electrodes and where they are attached. All right. So as I said, ECG is basically you taking a photo of the heart from different angles, right? So let's say that we place that guy, that camera, at the positive electrode, and it's taking a picture from there. All right. So it's going to see what is it going to see? It's going to see that a wave of depolarization it's coming towards it. And so on the ECG is going to represent it as a deflection going up, an upward deflection or a positive deflection. All right. So again, we're taking a photograph of the heart from the positive electrode. That's what you have to focus on, right? So as you saw in all the different leads, we have positive electrodes attached here, negative electrodes attached there, et cetera, et cetera, et cetera. But focus where the positive electrodes are attached, okay? Because we're going to put our camera that is taking in the picture of the electrical activity of the heart. We're going to put it at the positive electrode, and we're going to look at the heart from the positive electrode and see what's coming towards it, what's going away from us, et cetera, et cetera. All right? So we're going to mainly worry about the positive electrodes. Similarly, I gave you another example of repolarization, right? So we have a point here, we have a point here. This is the positive electrode, this is the negative electrode. Now we have a wave of repolarization spreading towards the positive electrode where we have put our camera to, to capture that electrical activity of the heart. So logically speaking, where is the deflection going to be, up or down? It's going to go down, right? So it's going to go down, all right? So that is important, and I hope it's clear. Any questions up until now? Please go ahead and ask. All right. Okay, excellent, very good. Okay, so now what we're going to do now is that we're going to apply all the concepts we've learned, and we're going to put it into one picture. This picture right here. All right. So we talked about a bunch of leads, right? We talked about like 12 leads. We talked about they have positive and negative electrodes, and then we said that we have to mainly focus on the positive electrodes because that's where we're going to take that electronic or electrical photo of the heart with our cameras, quote unquote cameras, right? And so once we do that, once we've done all that, once we've attached all the electrodes, it comes down to this. If this is the heart, if this is the axis of the heart, this is where the depolarization wave is spreading, the leads are looking at the heart from these angles or from these vantage points, you can say. They're observing the heart from these points, all right? AVR looks at the heart more towards from the right side. 2, 3, and AVF look at the heart from inferior or from below. 1 AVL are looking at the heart from the left side. V1, V2, V3, V4, V5, V6 are looking at the heart from the front, okay? And V5 and V6 are more towards the lateral side, so left lateral. V1 to V4 are more towards the front, okay? Again, What did I say? What is an ECG? It's looking at it's taking a photo of the heart from different angles. I said that in the very beginning, right? And we're applying that concept here. We have different leads, and what we're doing is that we're taking a photo of the heart from these different angles, or from these different, you can say, observation points. And once everything is done and dusted, everything is like figured out in terms of where the electrodes are attached, we find that AVR looks at the electrical activity. In other words, AVR captures that photo from the right side. Okay, so it's looking. So basically, you can see if this was an eye or this was a camera, it's looking at the electrical activity from here. Okay, 2, 3, and AVF are looking at it from below. Okay, so you can just imagine those camera guys and these positions and pointing towards these positions. 1 and AVL are looking at it from the left. Okay, and everyone's pointing towards the heart, right? Because that's that's the main thing here. And these guys are looking at it from the front, basically. All right. So let's elaborate on that. Each lead is looking at the same electrical activity from a different point, right? It's the same kid with the same bicycle, but we just have different points at which we're observing it from, right? So it's the same heart. Everyone just has one heart, which has the same depolarization, same repolarization that's happening every cardiac cycle. All we're doing with an ECG is that we're looking at the same electrical activity from different perspective, from different vantage, from different observation points, which I've talked about here. All right. Now let's apply another principle that we've learned. Let's say that we have, so as I said earlier, right? So generally speaking, the wave of depolarization, the wave of electrical activity that goes on in the heart, mainly speaking, it's going in this direction towards the apex, along the anatomical axis of the heart, right? So let's say that I'm looking at, let's say, I'm looking at the heart from this angle right here, from this point right here. So I'm taking a photo from here. On the ECG, tell me, if the wave of depolarization is spreading like this, is the deflection going to be up or down? Exactly, it's going to be down, right? Because when I said that we're taking a photo of the heart, the electrode that we're talking about is positive electrode. Let's say the positive electrode is here, right? And if the wave of depolarization is spreading away from the positive electrode, the deflection is naturally going to be down, right? It's going to go down. All right. Now, let's say that we have another guy right here who's taking a photograph from the heart from, let's say, the inferior lateral perspective, or from the inferior lateral point. So let's say he's taking a photo from here. Now, if the wave of depolarization is spreading in this direction, which is the natural direction, is the deflection on the ECG going to be up or down? Exactly, it's going to be up. Why? Because the point where we're taking the photograph from is the positive electrode, and the depolarization is spreading towards that photograph, towards that camera, towards that positive electrode, the deflection is going to go up. All right. And so you will find that, okay, we'll talk about that later. So we have a question here that says, don't we need to know where the positive and negative electrodes of the AVR lead are? Yes, of course. You need to know where they're attached, right? And once you know where they're attached, you have to, I think, the way that it works is that you have to figure out a way to correlate the attachment of the electrodes to the wave of depolarization by working out some vectors and stuff. All right. So in my opinion, you don't need to know this. All right. You don't need to know like how do the vectors work. Just know that we have different leads that look at the electrical activity of the heart from different perspectives. What are those perspectives? These are those perspectives. AVR looks at it from the right side. 1 and AVL look at it from the lateral side, left lateral side. 2, 3 AVF look at it from the below. V1 to V6 look at it from the front, with V5 and V6 looking at it from more towards from the lateral side, and V1 to V4 looking at the heart from more of the from the front side. Okay. So it depends on where they're attached to. So we know if it go. Of course, it depends on where they're attached, right? And so this is why I simplified it all for you and gave you this diagram right here, right? At the end of the day, it all kind of trickles down to this diagram here. Regardless of where the AVR positive and negative electrodes are attached, in the end, it's going to look at the electrical activity from this vantage point, from this observation point. Think of it like this. The positive electrode of AVR is here. which is in fact true, by the way. The positive electrode of AVR is attached to the right arm, and this is the right side of the body, right? The positive electrode of the AVF is attached where? To the left foot, and this is the left foot, right? Same goes for 2 and 3 leads. The positive electrodes of leads 2 and 3, I believe, are attached to the left foot, and so this is where they are. Then the positive electrode of the lead 1 is attached where? To the left arm, right? And this is the left arm. So it's this, it kind of goes hand in hand, but at the end of the day, this is the diagram that's important, because if you think too much about it, it's going to become complex. All right. Is AVR always negative? Sorry. In a normal ECG, if you attach it right, yes, AVR QRS complex will be negative. Why? Because it's going to go away from because it's looking at the electrical activity, just going away from it, basically. All right. They all kind of look upward deflection to me. How does an ECG have downward deflections? Let us talk about that in a while. All right, that's an excellent question. I had the same question, trust me, right? And we'll talk about that when we talk about specific waves. And then once we review the 12-lead ECG at the very end, what I'm going to do is I'm going to pick out specific points and tell you, okay, why is this positive here and why is this not positive on the other side, right? Remember, it's the same heart, it's the same electrical activity. All we're doing it as we're taking photographs from different point of views. That's it. All right, these deflections, they don't mean anything. At the end of the day, it's the same, depolarization, repolarization. All right. So we're just taking photographs. We're just taking the photographs of the electrical activity of the heart from different points of view. While in actuality, it's the same heart with one true wave of depolarization. Whether we record it from here or here or here, that's up to us. All right. And the results of that will depend on where we record it from, as I've shown here. So is everything clear so far? Any questions, any queries? Okay, we'll move forward now. Right, now we're going to talk about the actual ECG, right? So I hope the concepts were clear to you guys, all right? And we will repeat these concepts when we talk about the different components of the ECG. So let's start. So before we start talking about the specific P, Q, R, S, T, and all that stuff, let's define some things, all right? So you will find the word wave being used. The word wave means any deflection of the isoelectric line. So if it goes up, if it goes down, if it goes up, if it goes down, then up, and then down again and back, that's a wave, okay? So a wave is basically any deflection of the isoelectric line that you see on the ECG, right? And some waves, what they do is that because they're clumped together, they form something called complexes, right? Like let's say the QRS complex. It's Q wave, R wave, and S wave. Q deflection, R deflection, S deflection. Together, they form the QRS complex. A segment is a line between waves, but it excludes the waves. So a segment is an isoelectric line, which means it has to be horizontal. All right, it's between the waves. It's between the waves, but it does not include the wave. All right, naturally, because if it included the wave, then it would not be a horizontal line. So a segment is a horizontal line, an isoelectric line between waves, but excluding the waves. An interval includes a segment. All right, so the segment is the same definition earlier, and then it includes one or more waves. All right. Let's take some examples here. So we have, let's say, the P wave, the Q wave, the R wave, the S wave, the T wave. All right, could be a positive wave, it could be a negative wave. It's a wave. All right. And then we have complexes like the QRS complex. All right. Then we have the segment, which is a line between the waves, but it does not include the wave. So the PR segment, as you can see, is an isoelectric line that is between the P wave and the Q wave. But they call it the PR segment. I don't know why they should really call it the PQ segment, but everyone just calls it the PR segment. And it does not include the wave. It's an isoelectric line between the waves, but does not include the wave. We have an ST segment, which is between the S wave and the T wave. It's an isoelectric horizontal line that does not include the wave, but is between the waves. Then we have intervals. We have the PR interval that starts from the beginning of the P wave to the start of the QRS complex. Again, it should be called the PQ interval, but everyone just calls it the PR interval. It includes the PR segment, so it includes a segment, and that includes a wave. The wave that PR interval includes is the P wave. All right. Then we have the QT interval, which is start from the Q, which is at the start of the Q wave, and it ends at the end of the T wave. It includes the QRS waves, it includes the T waves, and it includes the ST segment. All right. So these are but just definitions just to help you clarify what is an interval, what is a segment, what's a wave. All right. So I hope this was clear. Okay. And before we move on, just know that we are going to use lead 2 as the standard lead to study everything from now on. All right. So what, when you see an ECG like this is most likely taken from the lead 2. Okay. That's like the standard characteristic cliche look of an ECG that you find everywhere, basically. All right. And if you remember, the lead 2 is basically looking at the electrical activity from below. All right. It's looking at it from below. Remember that this is our lead 2. So our cameraman is going to be here. All right. Okay. Before we begin, one more concept is that if you remember from your anatomy, or I don't know if you took it in anatomy or histology, if you look at the heart, it has the epicardium, which is on the outside. Then we have the myocardium, and then we have the endocardium. Is this clinical too, or are we just going to use describing it with lead 2 in this lecture, or do doctors generally look at lead 2? So when you have a 12-lead ECG, right, at the very bottom of that 12-lead ECG, you will find something called the rhythm strip, all right, or the rhythm strip. And most of the time, the rhythm strip is actually lead 2, all right. So yes, for me, when I read an ECG, of course, you have to be very holistic in how you read an ECG. But at the end of the day, to determine, like, say, the rate and regularity of an ECG, I always look at lead 2. But that doesn't mean that you forget about the other leads, because we can have something catastrophic happening in lead, let's say V5 and V6, and lead 2 looks completely fine. Okay, so look at all the leads basically. But for the purpose of simplicity, we're going to focus on lead 2 here. All right. So depolarization, as you know, happens from endocardium to epicardium. So the waves of depolarization, and histologically speaking, is going to spread from endo to epicardium, and repolarization will be the opposite. It's going to spread from epicardium all the way to endocardium. Okay, just remember this point right here. It's going to become important later on. So let's focus on each of these, waves and segments and intervals. The first thing is the P wave. All right, the P wave represents atrial depolarization. So we have the SA node that sends out the impulses to the atrium. All right, so the atria are going to now depolarize. All right, so the general, you can say, summated vector of atrial depolarization is going to point in this direction. It's going to point towards the apex, right? It's going to point downwards. And where is our lead 2? Where is our cameraman for lead 2? He's looking at the heart from down, right? So if we have a wave of depolarization, coming towards me, is this going to be a positive deflection or a negative deflection? On lead 2, we're just talking about lead 2. It's going to be positive deflection, right? This is why P wave is upwards. P wave is up, right? So you see the P wave is up. Does that make sense? Right? Again, we're just talking about the electrical activity of the heart. Don't worry about contraction and stuff like that. All right. So if we're looking at it from here, wave of depolarization coming towards me, I'm going to go up. So that P wave is up. All right. So this is the P wave right here. And this is just on the diagram to emphasize that the wave of depolarization is going to spread, from here to here, basically downwards. All right. After the P wave, we have P wave is a measure of the, so the P wave is not just a measure, it is the depolarization of the atria. All right. So it represents the depolarization of the atria. You're absolutely right. Okay. Next up, we have the PR segment. The PR segment, as you know, it's a segment, so it's an isoelectric horizontal line between the waves, but does not include the waves. And the PR segment basically represents the delay that we have at the AV node. So please go back and review the electrophysiology of the heart, where you will find that there's a delay at the AV node that we have to have before we, excite the ventricles, and that is represented by the PR segment. So this segment right here. All right. Next, we have the PR interval, which is from the start of the P wave to the start of the QRS complex. All right, we call this the PR interval. So the PR segment plus the P wave. I think that's pretty clear. So P wave plus the PR segment makes up the PR interval. It basically represents atrial depolarization plus the delay at the AV node. So it's basically the summation of the two things that we talked about earlier. Okay, so it's just the time between the start of the atrial excitation to the start of the ventricular excitation. So as we know, atrial depolarization or atrial excitation starts here and ventricular excitation starts here. Between them, we have something called the PR interval, all right? And usually it's 120 to 200 milliseconds. For your ease, on an ECG, it should be between 3 to 5 small squares. All right. We have a question that asks me to repeat the Pwave. All right. Again, Pwave is basically, forget about the Pwave just for 1 second and think about the electrical activity of the heart, right? It starts off with the SA nodes sending out waves of depolarization towards the atria, right? Now, the waves of depolarization, once you, let's say, add them together, mathematically, physics-wise, all that stuff, you don't need to know it. Once you add them together, you're going to find that all the waves of depolarization summated are going to point downwards and towards the left, basically towards the apex, right? So if we have the electrode, which is positive electrode of lead 2, looking at the heart from below, and we have a wave of depolarization spreading towards me, I'm going to have a positive deflection, which is known as a P wave. Is that clear now? Okay, very good. So we talked about the P wave, the PR segment, and the PR interval. Now we're going to talk about, we're now going to move on to ventricular depolarization, right? So just to review what happens again, is that, remember we had so we depolarized the atria, we had the delay at the AV node, and now the AV node is going to transmit the signal to the bundle of His, which will transmit the signals to the bundle branches, which will then go towards the Purkinje fibers and then finally towards the ventricles, right? So, but just remember that before we go to the ventricles, we have to pass through this structure right here. What is this structure in the middle? Put your anatomy hats on. The IV septum, very good, the intraventricular septum, all right? Okay. Now, so ventricular depolarization is going to be a little bit more complicated than atrial depolarization. And this is why we have a whole complex. We have a Q wave, then we have an R wave, then we have an S wave. So it's a QRS complex, right? Okay, so let's start to build the QRS complex. We'll start with the Q wave, all right? Again, we're looking at it from lead 2, not AVR, not AVF, nothing other than lead 2, all right? So in the beginning of the ventricular depolarization, the first thing that is depolarized is actually the intraventricular septum. All right. And the natural way, so don't ask me why is this, the natural way that the intraventricular septum is depolarized is from left to right. Okay. So it depolarizes in this direction right here. Okay. From left to right. So now if I ask you, if I'm taking a photo from lead 2, if I'm looking at the heart from lead 2 point of view, and I have a wave of depolarization that is spreading in this direction, is the deflection going to be up or down? Exactly, it's going to be down, right? Because I'm looking at it from here, and I have a wave of depolarization that's kind of spreading in an opposite direction, right? It's going right and down, so it's going in the opposite direction, and this is why the Q wave is a negative deflection in lead 2, right? So it's going to be a negative deflection, and that's known as the Q wave. That's the Q wave right there. All right, it's a negative deflection. Then we have the R and S wave. All right, so now the rest of the ventricular depolarization happens like this. So the rest of the depolarization, as you know, happens from the endocardium to the epicardium, right? So it spreads in this direction, spreads from here, as you can see these green lines, and now I'm turning them into red lines. Basically, this is how the ventricular depolarization happens, right? And so if you summate all of this at this point in time, as you know, we have a deflection that is going to be positive because the summated vector is going to be pointing towards lead 2, right? So it's going to be positive, and this is known as the R wave, all right? Now it becomes a little crazy now, just bear with me, right? Towards the end of ventricular depolarization, what happens is that the vector starts to point up and in the opposite direction. It's just the way that it is, right? So towards the end of ventricular depolarization, we still have to depolarize it. We still have to depolarize these points right here, right? So when we have to depolarize these points right here, as you can see, the wave of depolarization is kind of spreading upwards. And when things start to spread upwards, guess where the deflection is going to happen? It's going to go down, right? So if you go a little bit further, the vector completely changes direction. The summated vector, the summated direction of the depolarization completely changes direction. And so we have something called the S wave. It's a negative deflection, all right? Is this clear so far? A question that asks to repeat the Q wave. All right, sure. Okay, let me just repeat from Q, R, and S, the whole thing, all right? How do I clear? All right. So when we start ventricular depolarization, what happens is that first of all, we have to depolarize the interventricular septum. All right. And the way that the interventricular septum depolarizes is that it depolarizes from the left to the right side. So if this is the, the septum, the wave of depolarization, if we add up the waves, of the depolarization, if we add up the waves of the electrical signals, they're actually going to point in this direction. Now, if I'm talking about lead 2, which has the positive electrode here, all right, if I'm taking a photo from here, and if I have a wave of depolarization that is spreading away from me, that is spreading in this direction, I am going to have a negative deflection, all right? And that's the Q wave, okay? So the Q wave is basically the depolarization of the interventricular septum, all right? Does that make it clear for you? 221684? Excellent. Now let's talk about RNS, all right? So in RNS, what's happening is this, right? So we have, now we've depolarized the interventricular septum. Now the wave of depolarization is going to spread to the rest of the ventricle, all right? Now, as it spreads through the ventricle, it's going to spread from the endo to the epicardium, right? And if we add up those waves of depolarization, we find that in the initial stages, they're going to point downwards towards the positive electrode of lead 2. And as we know, if the wave of depolarization is coming towards the positive electrode of lead 2, where is the deflection going to be? It's going to be up, and that is known as the R wave. So it's going to go up, which is known as the R wave. Right now, as we depolarize more and more of the ventricle, we find that the depolarization waves have to spread a little bit upwards to depolarize these parts of the ventricles, right? And so when they move up and we summate their vectors, we add them up together and we look at the direction, we find that they are going to point upwards and upwards slightly. And as they do that, the deflection is going to become negative because I'm still at lead 2 and I'm looking at the ventricles from here, and the waves of depolarization are spreading away and away from me, and which is why I get the negative deflections until I get the actual S wave. So this is the S wave, all right? Is this clear? For 231507? Who asked to repeat the RNS wave? All right. We have a question that asks when the signals reach bundle of His, the Q wave. You can say that. Yeah, you can say that. All right. So we said that the P wave is atrial depolarization, right? What is QRS complex? It's ventricular depolarization, right? So it's ventricular depolarization. In addition to that, it's also atrial repolarization. So remember when we depolarize the atrium in the P wave, we still have to repolarize it, right? We still have to go back to the resting membrane potential to complete one cardiac cycle. And so atrial repolarization actually happens during the QRS complex. And because the QRS complex is coming from the ventricles, which are huge and more muscular, much more muscular than the atrium, they're what you see on the ECG. You do not see atrial repolarization because it's hidden within the QRS complex. All right. And the QRS complex is usually less than 100 milliseconds. And for ease, it's less than 3 small squares. All right. Next, after the QRS complex, we have the ST segment, which is the isoelectric line between the S and the T wave. And this is when the ventricles are fully depolarized, but are not starting to repolarize just yet. All right. And if you correlate that to the action potential of the ventricles, it correlates to phase 2, which is the plateau phase of the ventricular action potential. All right. What do you think? Siham Kutub. What do you think, let's go back a little bit. What do you think is going to be the wave of deflection if we could see the atrial repolarization on the ECG in lead 2? Okay, that's a very good thought. I believe most likely it will be down, yes. All right. The question is, what would be the direction of, it's a hypothetical question, of course, then what could be the direction of deflection on an ECG if we could see the atrial repolarization? And so, yes, I believe it's going to be down because well, I'm not exactly sure how the atria are repolarized, because ventricles, the way that they're repolarized is actually from the epi to the endocardium. So it could actually be up, right? Because it's a repolarization going away from the positive electrode, which is basically the deflection might be up. All right, so I'm actually, to be honest, not too sure about this. Why don't you look at it and let me know, all right? But it's not important. No one's gonna ask you. All right, so we're done with the ST segment. Next up, we have the, before we move on, we have some questions. Is one cardiac cycle atrial depolarization and repolarization only, or also ventricular depolarization and repolarization? So cardiac cycle is going to start from atrial depolarization and it's going to end with ventricular repolarization. Basically, it's just from the start to the end. Okay. There won't be any hypothetical questions like this in exam. No, there will not be. But they are still going to ask you about, like, they're still going to ask you about the concepts, right? So they might talk about the electrodes, and if a wave of depolarization is spreading towards it or away from it, what is the deflection going to look like? They're still going to ask you, but they're not going to ask you things that are slightly unclear like you've asked with the atrial repolarization, okay? Let's talk about the T-wave. Now, T-wave, things are becoming a little tricky now, all right? We're still at lead 2, but remember, now the ventricle is starting to repolarize. Now, as we said, that repolarization happens from the epi to the endocardium, right? So it's going to happen in this direction. So if we add up all the, the vectors of repolarization, we find that they point in this direction. So if we have waves of repolarization that are spreading away from the positive electrode of a lead, what is the deflection going to look like? Up. Okay, it's going to go up. All right, so it's a wave of repolarization away from the positive electrode, because repolarization happens from the epi to the endocardium. Okay, so focus on the vector and then focus on where the lead is. What did I say about the ST segment? The ST segment is basically the isoelectric line between the S and the T waves. It represents the delay that we have before the repolarization. And if you look at the action potential of the ventricles, you'll find that it correlates with phase 2, the plateau phase. Nothing is happening here, not depolarization, not repolarization. This is phase 2, basically. All right, so I think this is a very high yield point to know. All right, next up, we have some other intervals, all right, that are actually quite clinically important. We have the QT interval. The QT interval is from the beginning of the Q wave to the end of the T wave, QT interval, all right? And it's usually 350 to 430 milliseconds. So it's beginning of the ventricular depolarization to the end of the ventricular repolarization, all right? And before we move on, someone had asked me to recap. I will see if I have a slide for that. Okay, I will recap it in a bit, okay? Let me just review some pathologies that were mentioned in your lecture. We have PR interval. PR interval is from the start of the P wave to the start of the QRS complex. And if we have a PR interval prolongation, it suggests that it might be some sort of damage to the AV node, all right? So just imagine, if the AV node is damaged, it might prolong the delay that it usually has, so that prolongs the PR segment and eventually prolongs the PR interval as well. All right, so think logically. The ST segment is very, very important, especially in an ER, because the changes in ST segment may represent a myocardial infarction, which is basically, cessation of blood supply to the myocardium. The ST segment may be elevated, which is known as an ST segment elevation. The ST segment might be depressed, which is known as an ST segment depression. Okay, so it might be elevation, might be depression, and they may represent myocardial infarctions. Okay, so we have different types of myocardial infarctions, which I don't believe are important at your level right now, unless you've talked about them. We have something called the STEMIs, we have something called the NSTEMIs. The STEMIs are ST elevations, myocardial infarctions, and NSTEMIs are basically ST segment elevation myocardial infarction. So they found out that if a myocardial infarction has ST elevation, let's just put that as a separate category, because they are likely to have a worse prognosis, because this is something more severe, as opposed to an NSTEMI, which is a non-ST elevation myocardial infarction. Not so important for you guys right now. Then we talked about the QT interval, which is from the start of the QRS complex to the end of the T wave. QT can be prolonged by many things. It can be prolonged by medications, antibiotics. It can be prolonged by congenital syndromes, such as the long QT syndromes. okay? And it can be prolonged by actual myocardial infarction as well. So this is some of the causes of QT interval prolongation. So just know them, they're just recall at your level, but once you reach year 3 and eventually year 5, inshallah, these are going to become more and more important, and you're going to be focused on this rather than all the vectors that we've talked about so far. All right. Okay, there are some other segments and intervals that are mentioned in your lecture, which I'll just try to just mention them. The RR interval is from one R wave to the other R wave. All right. And you can use this to calculate the heart rate. So it's from it's basically the time between heartbeats. All right. It's the time between the heartbeats. The TP segment is from the end of the T wave to the start of the next P wave. And this is when the heart is totally quiescent or totally quiet, no electrical activity. And, mechanically speaking, which we've not really focused on too much, is diastole. All right. Is diastole. All right. So this here is the 12-lead ECG. And let me just recap some of the things, basically, let's just recap everything from the beginning, from the P wave, right? So we start with the P wave, right? Keeping all the concepts that we've learned so far in mind, we find that if during atrial depolarization, the wave of depolarization spreads in this direction, okay? We have found this to be true. Why? Mathematics. We don't need to know why, okay? This is the way that it is, all right? You don't need to know how to calculate all that stuff. But we know that the wave of depolarization of the atria is spreading in this direction. And if I look from the perspective of lead 2, I find that it's coming towards me. If it's coming towards me, if a wave of depolarization is coming towards me, I'm going to go up on the ECG, right? So P wave is a positive deflection. So that's a P wave. All right. P wave. All right. The PR segment. So after the P wave, we have the PR segment, which is a delay at the AV node. Since this is a delay, there is no electrical activity. It's an isoelectric horizontal line, no deflections, no electrical activity, right? Then we have the PR interval, which is basically just a combination of P wave and a PR segment. Basically it represents the time between start of atrial excitation to the time of, to the start of the ventricular excitation. Why does P wave have a part that's going down? It does not have a part that's going down. Where is that part that's going down? In the lead 2, P wave is completely positive. Upside U, where? I don't see it. Here or here? Habibi, that's a positive deflection. Positive deflection. Okay. I see what you mean. Why is it that it goes up, then it goes back down? Again, go back to the initial concept that we learned. Once we have the whole atria depolarized, there is no electrical difference between one part of the atria and the other part of the atria, right? And so if there's no electrical difference, there's no voltage. That's why it kind of dies back down. Remember when I talked about the deflection dying back down? This is what it is. Good question, though. Okay, that's the P wave. Then this is the PR segment, PR interval. Ventricular depolarization, as we know, starts out with the intraventricular septum depolarization, which actually spreads in this direction away from V2, which is why we have a negative deflection, which is known as the Q wave. All right. Then we have the R and S wave, which are, the R wave is positive because the rest of the ventricular depolarization is actually towards spreading towards lead 2, which is why we have a positive deflection. And then we have a negative deflection again, which is known as the S wave, because towards the end of ventricular depolarization, some of the waves actually spreading away from lead 2. And by remembering the concepts, it's going to be a negative deflection known as the S wave. All right. The QRS complex in its entirety, it's talking about the ventricular depolarization and the subtle, unobservable atrial repolarization. The ST segment is the isoelectric line between the QRS complex and the start of the T wave. It represents the plateau phase of the ventricular action potential, which is the phase 2 right here. Okay. Then we have the T wave, which is ventricular repolarization. And because ventricular repolarization happens from the epi to the endocardium, the directions are away from the lead 2, they're away from the camera. And so if a wave of repolarization spreads from away from the positive electrode, we have a positive deflection. And this is why the T wave is also positive. All right. Next, we talked about the QT interval. which is basically everything from start of the Q waves to the end of the T wave. All right. Now we talked about some of the pathologies. So I hope I reviewed everything for someone who asked about it for 230586. A couple of other questions. Is there an optimal duration length for RR interval? And if yes, should we know it? Honestly, I'm not sure what's the optimal RR interval, but eventually what it trickles down to is that you use the RR interval to calculate the heart rate, and the normal heart rate is between 60 to 100. So if you have, I can't recall from the top of my head, but if you can calculate it, you can actually calculate the RR interval at 60 beats per minute and the RR interval at 100 beats per minute, and that should be basically your normal range. All right, Osama, sorry. Next question. So it depends on above or below the line, not according down or up. I'm sorry, I don't get your question. Next question. The T wave happens at the base, right? What does that mean? What do you mean happens at the base? Base of the heart. Not really, no. The whole heart is going to get repolarized. But since the wave of repolarization starts from the base and goes up, this is why we have a positive deflection on lead 2. So if you meant that the wave of repolarization for the whole heart as a summation spreads towards from the base upwards, yeah, that's okay. Yeah, that's that. You're right. You're right. Okay. The deflection. So we have a question that says the deflections depend on upward above the isoelectric line, not actually like if the line is going up or down. It depends on if it goes below the line or above it. So I think I know what you're trying to say here. So deflections. So like if we have, right, this is an upward deflection and this is still a downward deflection, right? But the wave itself, the entire wave is above the isoelectric line. So the entire wave is actually positive, okay? If we have a downward deflection like this, right? And then it goes back to the isoelectric line. I mean, it's still going up, right? The trace is still going up back to the isoelectric line, but the entire wave is still below the isoelectric line, which is still a negative wave, okay? All right. Don't think too much, okay? Please, ECGs, don't think too much. Otherwise, you're going to mess yourself up, all right? Just remember, P wave is a positive wave. Q wave is a negative wave. R wave is a positive wave. S wave is a negative wave. And T wave is a positive wave. Just remember it like this. Forget about, upward and downward deflections for each wave. That's going in too much details, all right? All right, so this is the 12-lead ECG, and I asked and told you guys that at the end of the ECG, usually there's a lead. Usually it's lead 2, but in this case, they have put it as lead 1. No, actually, it's lead 2, actually. It's not lead 1 because it's similar to this one. I think the other I is hiding in the R wave. So as you can see here, we have a positive P wave, positive R wave, negative Q wave. The S wave, which is negative, is very, very subtle here. And then there's the P wave, sorry, the T wave. All right, so now, as you can see that in some of the leads, let's say V1, V2, you'll find that, okay, let's start from lead 1, right? So lead 1, everything is positive, right? Lead 1, everything is positive. Lead 2, everything is positive. As we said earlier, lead 3 is very much similar as well. AVR is very different, right? Because it's looking at the heart from a totally different point of view compared to the other leads. Everything is going to be negative, right? So the QRS complex, the R wave is negative. Basically, the T wave is negative. The P wave is also negative because everything that we talked about lead 2, just make it opposite. And then you have AVR basically. All right. So normally speaking in AVR, things are negative, but it's still recording the same electrical activity just because it's recording it from a different point of view, just because it's taking a photograph from a different point of view. That's why things are a little bit different. Okay. And okay, so for the V leads, things are a little bit more difficult at your level. Okay, there is we have something called the biphasic wave and all that stuff, which I do not think that is important at your guys' level. So I think just focus on lead 2. All right. How can I tell if there's an elevation or depression in the ST segment? Again, this is not for your level, but if you go at the very end of the QRS complex, which is around this point here, which I believe is known as the J point, if I'm not mistaken. If the J point is 1 to 2 millimeters above then the isoelectric line, we call it an ST segment elevation. Okay. do not have to know this at all. Like you don't even have to know it in third year. All right. But if they were to give you an ECG with ST segment elevation, it would be very clear that the ST isoelectric line would be up here. So it's going to be like this, basically. It's going to be like this. Okay, again, so it's going to be like this. It's going to be clearly up. Okay. So okay, I'll tell you a trick to how to recognize it. And the one we'll talk about it more because he talk about the pathologies and stuff. But if the isoelectric line is here, right, just compare the ST segment to the isoelectric line. Is it above it or is it below it? If it's above the isoelectric horizontal line, it's ST elevation. If it's below it, then it's depression. Does that make it clear? Why is the isoelectric line in some kind of wavy? Because these are actual real life ECGs, and in real life ECGs, patients move, right? And when people move, that the ECG records it as electrical activity when it's not actually representative of what's actually happening in the heart. Okay, so you have to, if you're getting an ECG done, just be still. All right. All right, so as we're running a little short in time, so I'll just end with this important thing, which is correlating the electrical activity of the heart to the mechanical activity, which is systole and diastole, right? And so we talked about all of this. I will not go over it again, but just to recall, we have atrial depolarization, then we have ventricular depolarization, then we have ventricular repolarization, right? And I know you have a whole lecture on this diagram right here, this dreaded diagram. But let me tell you, this is such an important diagram, which shows up a lot of time in your board exam. So please be very good with this diagram. All right. So on this diagram, you find everything. You find the ECG, you find the heart sounds, you find the pressures, you find the volumes, you find everything, right? And so I like to quickly correlate, and I know you have a session on this tomorrow, but just quickly correlate. If you see, this is the Pwave, right? This is atrial depolarization. After atrial depolarization happens, after a little while, atrial systole starts to happen, right? Because the atrial still have to depolarize first, then they contract, right? And the contraction correlates with systole. And so if you look at the cardiac cycle, this wave right here, which is the A wave, represents atrial systole, right? As you can see, it happens a little bit after the P wave on the ECG. So P wave, atrial depolarization. After a little while, atrial systole happens, which is atrial contraction, right? And same goes for the QRS complex. Starts with the QRS complex is from here, but the actual ventricular systole happens a little bit later. Okay, and so yeah, that's it. This is another diagram that depicts it. So this is the P wave, which is atrial depolarization, right? But atrial systole doesn't happen at the very start of the P wave. It starts a little bit later because the atrium has to be depolarized before it starts contracting, right? So it's a little bit delayed. And same goes for ventricular systole, right? So ventricular systole should technically start here because that's when ventricular depolarization starts, right? But it is not because it takes a little bit time for the muscle to contract after it's received the excitation signals. All right. So yeah, last thing I want to talk about is this slide that's in your lecture. So we said that we are looking at the heart from different perspectives, right? And I gave you that diagram, which is AVR on the right side, 1 in AVL on the left lateral side, 2, 3 AVF looking at it from the bottom, V1 to V6 looking at it from the front, with V5 to V6 looking at it more from the lateral perspective, while V1 to V4 is more towards the center or the front of the heart, right? When looking at these leads, right, if 2 and 3 and AVF are looking at it from the below, most of the electrical activity that 2, 3 and AVF catches is from the below region of the heart. So if we have some abnormality in the inferior region of the heart, it's going to show up in 2, 3 and AVF. 1 in AVL and V5, V6, if you remember, are more lateral, right? So they're looking at the heart from the more lateral perspective. So if there's any abnormality in the lateral perspective of the heart, it's going to show up in 1 AVL, V5, and V6, right? If we have a problem in the anterior or the septum of the heart, is going to show up in V1 to V4. All right. Yeah, at your level, yes, this is memorization, unfortunately. Okay, this is memorization. In fact, and at all levels, this is memorization at the end of the day. But it goes back to the concept that I spent so much time teaching you guys, right? Inferior, so 2, 3 AVF is looking at the heart from the bottom, as I told you earlier, right? So the bottom pathologies are going to correspond to 2, 3 and AVF because it's mainly focused on the bottom of the heart. or looking at the bottom of the heart. Same goes for 1 AVL V5 V6 is looking at the heart from a more lateral left perspective, a left lateral perspective, right? So any abnormalities going on the left lateral side of the heart are going to show up more on 1 AVL V5 and V6. For the anterior and septal, so the anterior is basically V3 V4 and septal is V1 V2. It's memorization, I guess. Yeah. AVR is not here because no one really likes AVR. You know, AVR, no one really looks at it. I don't recall any specific pathologies that you can pick up in AVR specifically. Although I think I remember one, I may be wrong, I don't take my word for it. If we have a myocardial infarction that involves all the arteries, all right, the only reliable source would be to look at AVR, but this is again something too advanced. You don't need to know it, okay? What's CAS? Where's CAS? Oh, coronary arteries. Coronary arteries. Dextrocardia. What about dextrocardia? Oh, yes. Sure, yeah. Excellent. Dextrocardia. If we have dextrocardia, which is the heart pointing in the opposite direction, everything would be just reversed, right? Can be picked up on AVR. Yeah. Okay. All right. Radwan, would you like to continue now? We're talking about the RCA, LCX. Okay, RCA is the right coronary artery, LCX is the lateral circumflex artery, LAD is the left anterior descending artery, and LAD is also the left anterior descending artery. Okay, now these arteries, so this goes back to your anatomy, this is not physiology. These arteries supply specific areas of the heart predominantly, okay? Placement of the leads, no. What do you mean placement of the leads? This is arteries, it's the coronary arteries. And I know this doesn't make too much sense because how are we relating arteries to leads, right? Okay. The reason that they've divided into inferior, lateral, anterior, septal is mainly because of myocardial infarctions or heart attacks, right? So when we have heart attacks, we have involvement of specific arteries. And sometimes we have involvement of all the arteries, but sometimes we have involvement of specific arteries like the LCX or the LAD or the RCA, right? So let's say if I have involvement of the RCA, let's make it easy because RCA is kind of weird. Let's say if I have involvement of the lateral circumflex artery, which supplies the lateral aspect of the heart, right? Which supplies the lateral left ventricle. If I have LCX or lateral circumflex artery blockage and I get a myocardial infarction in the lateral left aspect of the heart, which leads are going to pick it up? Exactly. So the lateral leads, so 1 AVL V5 V6. So that represents that, oh, the lateral left side of the heart is more involved, and so probably the LCX artery is involved. All right. And you can apply this to the other arteries as well, the LAD, the RCA, etc. Okay. Any questions? You are very welcome. Radwan, yes. Would you like to continue from here? I have, I think, a few slides on reading an ECG, but I think you can do it maybe because I took too much of your time.
Thank you, Safwan, so much. But would they like to take a break first?
Guys.
All right, so maybe a 10 minutes break. We come back at 8:40.